Okay, welcome students to another lecture about complex number. This lecture about Cauchy Riemann equation and harmonic function. We study two topics in this lecture. So start by the definition. If we have any function w is equal of z, so we say that this function is differentiable or analytic function if satisfy the Cauchy Riemann equations. The condition of Cauchy Riemann equations, two equations. The first condition is the partial derivative del u over del x is equal del v over del y, and second condition is del u over del y is equal minus del v over del x. So if you find the derivatives, the function u with respect to x and y, and find the derivatives of the function v with respect to x and y also, and satisfy these two conditions, we know about Cauchy Riemann equations. After that we can say that this function is differentiable or analytic function. Okay, let's see these examples. In this example, consider if z is equal to z square. So we need to find, the question here is to find the points of anywhere u and phi satisfy Cauchy Riemann equations. To solution this example, we start by the function if z is equal to z square. After that, remove z, because any complex number z we can represent by x plus iy. So this is equal to x plus iy square. So from this function term we get x square plus 2x yi minus y square. After that, to find or to gather the real parts of this function and imaginary parts. So we have this first term x square minus y square, this is real part of this function, and plus 2xy is imaginary part of this function. So the function u is equal to x square minus y square, because this is the real function, and imaginary function v xy is equal to xy. Now find the derivatives in a function. So we start del u by del x is equal to x, because the derivative x square is equal to x, and the derivative del v with respect to dy is equal to x. So the condition is equal to x is equal to x. So this is function is correct for all points in complex number xy. For the second condition, we find del u over del y is equal to minus y, and minus del v over del x is equal to minus y. So we get this result also, minus 2y is equal minus 2y. So satisfy all points in complex number. So this is the function if z is equal to z square, satisfy the condition of Riemann condition. Okay, so this is analytic function or is differentiable function. For the second example, so this function is ready, find by u and phi. So the part of u xy is equal x power 3 plus 3x square y minus y cube minus x square minus 2y square. So this is the term x cube plus 3x square y minus y cube minus x square minus 2y square. This is the function u xy, because this is the real part in this function. So second part, imaginary part, with respect to the function vxy, we have minus x cube plus 3xy square minus y cube plus 4xy plus 3y. So the question here, find where f is differentiable and give derivative where it is exist, or we can say that another expression is to find the point of all anywhere u and phi satisfy Cauchy Riemann equation. For the solution in this example, we determine the function u and determine the function phi from the given equation. So after that, try to apply the Cauchy Riemann equations. So this is the first condition, del u over del x is equal del v over del y. So del u over del x is equal, we have here x cubed, so the derivative of this 3x square. Second term we have 3x square y, so the derivative of this 6x y. For the another term y cubed, this term is not dependent on x, so the derivative is equal to 0, minus x squared, so the derivative of this term is minus 2x, and 2 minus 2y squared, so this is not dependent on x, so this is the derivative is equal to 0. So we get del u over del x is equal to 3x squared plus 6xy minus 2x, and follow the derivative del v over del y for the function. So we have del v del y, so we have minus x cubed, not dependent on y, so the derivative is equal to 0 here. And second term we have 3xy squared, so the derivative of this term with respect to y is equal 6xy, so we have minus y cubed, so derivative here minus 3y squared plus 4xy, so this derivative is equal 4x with respect to y plus 3. Also, for the second condition in Riemann equation, we get del u over del y and del v over del x, so we get del u over del y 3x squared minus 3y squared minus 4y, and del v or for del x is equal minus 3x squared plus 3y squared plus 4y. So apply the result del u over del y, we get this result, the x squared minus 3y squared minus 4y. So this is satisfied for all z belong to C4. We say that here for the first part of Cauchy-Riemann equation, we have del u del x is equal del v by del y, so del u is over del x 3x squared plus 6xy minus 2x. So it is not equal del v by del y. So until this function to satisfy Riemann equations, we suppose that this is equal. So suppose that is del u over del x is equal del v by del y, because we need to say that when this function is satisfy the condition of Riemann equation. So remove del u over dx and del v by del y and put the result in the previous slide. So we get this is 3x squared minus 6x minus 3y squared plus 3 divided this equation about 3. So we get this x squared minus 2x is equal minus y squared plus 1. Completing the square here to get x squared minus 2x minus 1 plus 1 plus y squared minus 1 is equal to 0. So we get this result. That means this condition satisfy when x minus 1 squared plus y squared is equal to, so this is circle equation, a circle equation. For the second part in the question, when the derivative or where the derivative exists, f is. So the condition here is equal f prime z is equal del u over del x is equal I del v by del x. So find the result of del u of del x, so this is the result of del u by del x plus I, and represent or consider the favor dx by the previous result. So we have minus 3x squared plus 3y squared plus 4y. So we have now another definition. We talk about this when this is the question here is when the function uxy is a harmonic function. So if you need to check the function is harmonic, so we applied this definition. This definition, a function u from r squared to r is harmonic if and only if del square u over del x squared plus del square u over del y squared is equal to 0. So that we find the second partial derivative with respect to the function u with respect to x, and second partial derivative u with respect to y, and add this two partial derivative. If is equal to 0, we say that this function is harmonic. So this condition also known as Laplace equation. So this equation is called also Laplace equation. Of course, this derivative are continuous function. So we have this remark: if f is equal u plus I phi is analytic function, then u is a harmonic function. And conversely, we have this second Riemann: if u is a harmonic function, then there is a function phi such that f is equal to u plus I phi is analytic function. So this is like theorem. So if you have analytic function, you can deduce u is a harmonic function. Analytic function, you can deduce u is a harmonic function. Conversely, if u is harmonic function, you can deduce if u is analytic function with respect to some function v. So this is example to illustrate this concept. So for this example, we have this function uxy is equal exponential function a s power minus x product x minus sine y minus y cosine y. So this is the question here: show that u is harmonic functions. If you need to show that u is harmonic function, to apply this definition, we need to find the first partial derivative with respect to x, and second partial derivative with also for x, and continue to find the first partial derivative of y and second partial derivative with respect to y, and after that try to find the addition between two terms if is equal to 0. That's mean harmonic function. So we say that the solution, we have ux is equal to del u over del x. So this is the product of two functions. Apply the rule of product for the derivatives. So we have e power minus x, so this is the first term, s minus, multiplied by derivative of second term. So the derivative x sine y is equal sine y with respect to x, plus we have here minus y cosine y, so this is constant function, so this is equal derivative, this term is equal to 0, plus second term x sine y minus y cosine y multiplied by the first derivative s minus x. So the derivative s minus x is equal minus e s minus x. So after that, simplify this formula to get this result: s minus x sine y minus x sine y plus y cosine y. So both this equation is equal to first equation. Now we need to find the second partial derivative u with respect to x. So again, apply the derivative for the equation 1. So we get this u x is del square u over dx square. This is equal s minus x. So the derivative the first, and this is the second derivative of second term minus sine y, plus second derivative multiplied by the first derivative. So s minus x minus e s minus x is derivative of a s minus x. So simplify this result to get s minus x minus sine y plus x sine y minus y cosine y. So add this is, we have minus sine y minus sine y, so this is get result 2 minus sine y plus x sine y minus y cosine y. So this is the second equation of formula of the second partial derivative of with respect to x. Now we find the derivative for the function u xy with respect to y. So this is the first partial derivative. Del u over del y is equal s minus x by the same y, product of two functions. So we get this result: s minus x cosine y minus y times minus y plus cosine y dot 1, because this is product two functions. So apply the rule of product of two functions, plus, so this is the second term multiplied by the first derivative s minus x with respect to y. So this is equal to 0. We get the equation 3: s minus x cosine y plus y sine y minus cosine y. Now again, try to find the second partial derivative u with respect to y. So we have del u square by del y square is equal s minus x. So find the derivative of second term. So this is x cosine y. So this is the derivative with respect to y. So derivative of cosine is equal minus sine y. So we get this term minus x minus sine y. So plus y sine y. Y sine y, this is two functions depend on y and the derivative with respect to y. So apply the result of rule product of two functions. So to get the first y, second derivative of sine by cosine, plus second term sine y product by derivative of y is equal to 1. So minus cosine y, this derivative minus cosine y is equal sine minus sine y, minus times minus is equal plus. So the second derivative multiplied the first, because we have this is equal 0, so this is removed. So we get this result is equal a power minus x sine y plus y cosine y plus 2 sine y. So this is 4 equations. Now to apply the condition, Laplace equation, we have equation 2 and equation 4 to make addition. So if you have addition, because you have uxx plus uyy, remove the value of uxx, put here s minus x minus 2 sine y plus x sine y minus y cosine x plus, this is the value of uyy, second partial derivative. After that, simplify by the product of terms, so we get this result. So we say that the all terms, because we have minus 2 s minus x sine y, this is the similar term plus s to minus x sine y by line of red color. So this is, we cancel these two terms. Also we have two terms here by line blue is equal the same, one positive and another one is negative, so we can cancel it. So the third term by green line, so this is minus y minus x cosine y is equal plus y minus x cosine y, the same, the first negative and the second positive. So this is cancelled with it to get the result is equal to 0. So that's mean if the result is equal to 0, that's mean the function is harmonic function. If the result is not equal to 0, so we say that ux is not harmonic function. So for this reason is equal to 0, right hand side of this equation, so we can say that ux is harmonic function. This is exercise. This function is equal uxy is equal xy, show that u is harmonic function. Apply the same method for the first example. Find the first derivative and second derivative with respect to y and with respect to x also, and add these two equations to get the result if is equal to 0. Okay, another example now. If we have function uxy is equal xy is harmonic now. So this is the function now given is harmonic function. So find harmonic conjugate phi xy such that if u plus I phi is analytic function. So to solve this equation, we need to say that this remark or not. So if z is equal uxy plus I phi xy is analytic if and only if satisfy Cauchy-Riemann equations. So what does mean satisfy Riemann equations? Satisfy Riemann equations, that means satisfy two conditions. Del u over del x is equal to del v over del y, and del u over del y is equal to minus del v over del x. So we need to satisfy or holds this condition. So del v by del y from the function is equal to del u by del x. If we find the derivative xy, so we get this is y equation. Y. So this is the first equation. So we need to seek or research about the function phi. Try to find the integral now. Find the integral equation 1 with respect to y. So the integral del phi by del y, when we take this integral del phi by del y, because the integral is opposite of derivative, so we get the result fxy. For the right hand side of this equation, integral y dy is equal 1 over 2y square plus constant function. So the constant function here gx, because we find the integral y, so we put the constant function is a function of x. Sometimes if we integrate the equation 1 with respect to x, we put the constant function g of y. So بمعنى إذا المعادلة، لاحظوا هنا بالعربي عشان لما نكامل للإف، إذا كاملت للواي نضع الدالة الثابت تكون بالنسبة للإكس، أما إذا كاملنا الدالة بالنسبة للإكس نضع الدالة هنا بشكل مغاير بتكون بالنسبة للواي. أوكي. الآن derivative equation 2 with respect to x. إذا كملنا للy, if we integrate the equation with respect to y, so find the derivative with respect to x. So del v over del x is equal this result, del by del x, the function y is constant is equal to 0. The derivative of gx, because this is unknown function, so the derivative just is g prime x. Since minus del v over del x del u by del y, so this is Cauchy-Riemann equation multiplied by this equation by minus 1 to get del v over del x is equal this. So now find the integral of this formula. So the del v over del x is equal g dash x. So this is equal minus x, so get this result. Equation 4, find the integral equation 4 with respect to x to get this result, minus x squared over 2. So this is gx. Now vxy is equal minus y squared over 2 minus x squared over 2. So if z is equal u plus I vxy minus 1 over 2 I ay squared minus x squared. Try to solve this example to find the function fxy by the same method of the first examples. إذا لو عملنا لكم هكذا في ملخص باللغة العربية، لاحظوا عندنا مفهومين، اللي هو مفهوم معادلة كوشي-ريمان، هذه المعادلة اللي عندنا شرطين اللي تحدثنا عنهم في المعادلات، اللي هو التفاضل الجزئي لليو بالنسبة للإكس والواي، وبنفس القدر المعنى نفاضل الفي بالنسبة للإكس والواي ونحقق الشروط. تتحقق معناه نقول أن الدالة هذه طالما أنها حققت معادلة كوشي-ريمان فهي دالة سميناها differentiable يعني قابلة للتفاضل، أو نسميها analytic function دالة تحليلية. المفهوم الثاني اللي أخذناه، متى تكون الدالة هارمونيك؟ تكون الدالة هارمونيك إذا كان نعتمد الآن على التفاضل الثاني في الهارمونيك وليس التفاضل الأول. في كوشي-ريمان نجد التفاضلات الجزئية الأولى. في الهارمونيك فانكشن يعني الدوال التوافقية، في الدوال التوافقية نعتمد على التفاضل الثاني، فلا بد نوجد التفاضل الثاني لإكس ونجمع مع التفاضل الثاني للواي. إذا ساوى الصفر في الحالة هذه تسمى الدالة توافقية. إذا كانت الدالة توافقية وتحققت معنا، ممكن الآن في صيغة السؤال السابق كيف نوجد الدالة V بحيث تكون تحليلية، ونتبع نفس الطريقة هذه. نشوف المتغير اللي فيه دل في باي دل إكس ونكامل الدالة بالنسبة للفي للواي، ثم نفاضل المعادلة الثانية بالنسبة للإكس ونساوي المعادلات حتى نستطيع أن نبحث عن الدالة في إكس واي اللي هي الجزء التخيلي، ثم نعوض بالدالة. يعني مثل هذا المثال اف زد يساوي يو زائدا اي في، فكانت الدالة يو هي عبارة عن إكس واي، والدالة في هذه إحنا اللي بحثنا عنها، الجزء الإيميجينري اللي إحنا نسميه الجزء التخيلي، اللي برضو نطلق عليه كونجيكيت هارمونيك، اللي هي الدالة التوافقية اللي احنا الكونجيكيت المرافقة بالنسبة للدالة اكس اللي هي يو. فنبحث عن الدالة في، وبعد ما نطلع الدالة في نعوض عنها ونوجد الدالة اللي هي اف زد. يمكن حل المثال الاكسرسايز هذا بنفس الطريقة. Thanks to follow me about this lecture.